recording, I guess, from now on.
Okay, excellent.
I'm the head of the institute here, so you'll be soon. I see your fellow here.
Yes, exactly.
So
yeah. Thank you very much.
I have to leave quickly after your talk, so.
Okay. Well, nice to meet you.
Yeah.
Okay. Thank you everyone for joining again to our Friday afternoon seminars. Thank you. So I'm very happy to introduce to you Earl Bellinger. So let me tell you a few things about him that I wrote on his resume. So he did his Master of Science in Indiana University. It was a master degree in computer science, not in physics, but in computer science. Then he moved on to do a PhD. It was a dual PhD, partly from the Max Planck Institute in Göttingen and partly at Yale University. Then he moved on. He already did 2 postdocs. So one he did at Aarhus University, if I remember well, and now he is at the at the Max Planck Institute in Garching. So his research field is asteroseismology, and that was also the topic of today. So please, Earl, you have the floor.
Thank you very much. It's a great honor to be here talking about asteroseismology at one of the premier asteroseismology institutes in the world. It's a little funny. It's like bringing coals to Newcastle to tell the people here about asteroseismology. But of course, there are some people here who work on other topics, and that's especially what I'd like to make a connection with today. What can asteroseismology do for you? So that's why I'll be talking about asteroseismic probes of stellar evolution and fundamental physics and other such things. Now, to start us off, yeah, of course, Connie wrote the book on asteroseismology, so we have to pay our respects. But in general, the people who you're probably used to hearing about in this respect are working on the more massive stars on the HR diagram, whereas my research is more focused on the lower mass stars and also some stars in the classical Cepheid instability strip. So hopefully, even among the astroseismologists in the audience, there will be something new. So I'm interested in the questions of how we can test stellar evolution theory. And if stellar evolution theory is correct, what can we do with that information? Of course, there's many things we can do, and I'll just highlight a few possible applications. Now, the first question is a bit funny for some people, because if you ask most people who don't work on stars, they say, well, of course, we've nailed stars. We understand how they evolve. All the major problems are solved. And it doesn't matter if you ask them in 2021 or if you ask them in 1865, they had that same attitude towards it. Lord Kelvin, of course, saying that the meteoric theory is certainly the true and complete explanation of the solar heat, which we nowadays, of course, know that it is in fact not. And he was so confident that his theory was right that he got Darwin to revise on the origin of species to take out his calculations involving the geological age of the Earth. So that motivates a bit wanting to test the theory and finding new ways to test it. Now, about 100 years ago, Eddington proposed that stars get their power from nuclear energy. And now we, of course, think that's the correct interpretation. But at that time, you know, they also produced HR diagrams where stars utterly failed to turn into giants. And so that didn't reproduce any of the observations. James Jeans, famous star formation theorist, wasn't happy with any of it, and he wanted to completely abandon ideal gas laws when talking about stars, and published a Nature article saying that stars are most likely liquids. Now, of course, along white dwarf cooling, there are some liquid phases, but for the most part, despite his very impressive HR diagram for liquid stars, which one must admit, it fits the data pretty well, we do not think that stars are liquids. Later on, the theory evolved into more or less its present form, and we got extremely impressive isochrone fits, for example, to clusters of stars. And that gave us increased confidence that the modern theory is in fact on the right track. But even when he published these impressive diagrams, he also made note that just getting the turns right through the HR diagram doesn't mean that we actually understand what's going on inside of the stars, because these are merely the external characteristics, the luminosity and the temperature of the star. And the internal characteristics could be quite different. And there was a pretty interesting, I think, demonstration of this in 2004 when it was shown that the hook in isochrones at the end of the main sequence can be reproduced with different input physics. One by including the effects of diffusion into your tracks, or alternatively by artificially extending the boundary of your convective core. You can get this isochrone hook in two different ways, which means the stellar interior is different, but the observable effects are the same. And so we want the ability to get past just looking at the twists and turns in the HR diagram and look inside of the stars. And well, I've probably already spoiled the tool we'll use that to probe those physics. That's of course asteroseismology. So in the 60s, researchers at Caltech observed the sun and produced this extremely impressive image showing that there are velocity fields in the solar atmosphere. These are, of course, the oscillations of the sun. And the fact that it was only discovered in 1962 should give you an impression of how small the amplitudes of the solar oscillations are and how difficult it is to observe these oscillations in any other star. Now, making use of these oscillations, it turns out that these are acoustic waves traveling through the interior of the sun. And what you probably remember from, for example, Connie's course or her textbook or any of the lectures that her students have given is that these modes can be distinguished by their spherical degree. So the number of 0 points on the surface. And you see the high degree modes are confined to the atmosphere or the outer layers of the star, whereas the lower degree modes will pass through. Now, these are P-mode oscillations in contrast to the G-mode oscillations that Connie's group is primarily concerned with that occur in the higher mass stars. And with these P-mode oscillations in the sun, we can observe about 200 degrees up to about 250. And with that, it's possible to resolve essentially the entire solar interior, from pretty close to its center point to pretty close to the surface. And from that, you can map out its internal structure, it's the stratification of its density, and also its sound speed and other such interesting things. And this turns the sun into a laboratory for stellar physics, and a laboratory for testing the physics of stellar evolution. And in this interesting paper from 1993, the JCD constructed solar evolution models with differing input physics, and in particular, including or not including the effects of diffusion. And what you can see on the y-axis is the difference in the internal sound speed, right? Basically the ratio of pressure to density inside of the sun, ranging from nearly its center to its surface point. And you can see that, first of all, that the helioseismic structure that's given by solar evolution models matches the observed structure of the sun within 1%. So that's a phenomenal triumph in astrophysics, to say that the theory is actually producing the correct internal structure of a star. The other thing you can see is that the inclusion of diffusion inside of these simulations dramatically improves the agreement between theory and observation. And so this tells us that we can use helio and asteroseismology to do fundamental tests of stellar physics. The other interesting thing here is that it doesn't actually agree. You don't get perfect agreement. Even today, with modern solar evolution models, near the base of the solar convection zone, you get something like a 60 sigma disagreement between theory and observation, which is mainly a testament to how exquisite the observations of the sun truly are. In In recent years, there's been a few space missions that have started detecting these oscillations in other stars. The best, from my point of view, has been the Kepler mission, which for 4 straight years stared at one fixed field of view in the sky and took an observation almost once per minute. And that allowed us to get exquisite observations of systems like 16 Sig, which is, it turns out to be a triple system, but it's, you know, the stars are highly separated, and so they seem like single stars, and the A and B components are, they're both almost like twins of the sun, a bit more evolved and a tiny bit more massive, but only marginally so. And so these are sort of like my pet stars. There's also 16 Sig C, but that's less interesting for me. It's a red dwarf. And 16 Sig B has an exoplanet, which is quite interesting. So what did Kepler do? Kepler looked at these stars, and here's a week of photometry from Kepler on one of those stars, and you don't really see anything, right? It's quite boring in the time domain, but as soon as you go to the frequency domain, then clear asteroseismic signal emerges. So for this star, we can see about 55 low-degree modes of oscillation. So before, when I showed you the solar observations, you could see modes up to a degree of 250, but due to partial cancellation effects of only getting the integrated light, we can only see modes up to L equals 3. But nature was kind to us, and these are the global oscillation modes. These are the modes that go very near to the stellar center. To give you an idea of what kind of distortion we're looking at, these are what quadrupolar oscillation modes look like. Now, of course, this is a highly distorted view. Stars don't have nearly this high amplitude, but if you were to pump up the amplitude, this is the kind of distortion you would see with an L equals 2 mode. Now, what can you see in this diagram is an extremely uniform pattern, which perhaps you've seen already. And what you can see is that basically modes of the same degree are separated nearly evenly in a quantity that we call the large frequency separation, which turns out to probe the mean density of the star. And then modes that are separated in degree by 2, like for example the radial and the quadrupolar modes, are also separated, but by a much smaller separation that we call the small frequency separation. And this turns out to be a proxy for the age, which I'll explain shortly. But yeah, you can also see the power is centered at a characteristic quantity that we call nu max. And just for your reference, us astroseismologists love to use the units of microhertz, but a frequency of 3,000 microhertz is a period of about 5 days. So what can we do with this information? Well, on the left, I've plotted an HR diagram showing some of the solar-type stars that were observed by Kepler. And on the left, I've shown a so-called CD diagram or asteroseismic HR diagram. It has various names, but I've just taken these two quantities that I've shown you in the previous slide and plotted them along with some theoretical models. Now, for these models, I've used the MESA Stellar Evolution Code, of which I'm now one of the developers as of about a year ago. So is Pablo Marchin in the audience. And so, yeah, if we take these observations of these stars and put them on this diagram, it's kind of interesting to see what happens here. And perhaps many of you have seen this already. So it turns out that the large frequency separation is, like I said, probing the root mean density of the star. And so for stars of fixed mass, as they evolve, the radius is evolving, and therefore the mean density is evolving. And so you can see its evolution in terms of the large frequency separation, along with the evolution of the star. So here are tracks separated in mass, and also as they evolve through the main sequence, their core hydrogen abundance goes down as it's converted into helium. And so you can see the evolution of the small frequency separation with the evolution of the star. And so this table can effectively serve as a lookup chart for a star. If you take a star, like for instance, I've taken all of these stars here and put them over here, and I've colored them by their spectral type. So these are the F-type stars, and then the G-type stars, and then this one K-type star. And you can see the uncertainties I've indicated in the corner. These are extremely precise measurements of the large and small frequency separation of order 0.1 microhertz or 1 microhertz, which allows us to clearly distinguish the ages and masses of these targets. So in a simplistic world, one could merely look up these values in some kind of table. Now, of course, these theoretical tracks are for one fixed set of input physics, one fixed set of composition. So if you do things like change the metallicity, change the initial helium abundance, the picture gets more complicated, which is why we've developed machine learning methods to connect theory with observation. And so in this paper, now quite a bit old actually, it was from back when I was a PhD student, what we did was we trained a machine learning algorithm, in this case a random forest, on an extremely large grid of models varied in, I think, 8 different input parameters: mass, age, initial chemical composition in terms of metallicity and helium abundance, the mixing length parameter, overshooting, undershooting, and diffusion. And basically used this more sophisticated lookup table to produce distributions of things like the age and mass from observations of solar-type stars. Recently, Mark Hahn and I expanded this work and used a convolutional neural network on basically mock observations of these stars, on a shell diagrams of these stars, as the inputs, and then on the outputs we use mixture density layers to get full posterior probability distributions. Okay, so given this methodology, how well can asteroseismology characterize stars? So here you can see the cumulative distributions of the different parameters that we can estimate. And these quantities over here are in the same order as these get stacked up. So this is for the surface gravity, and here are 97 stars that we've applied this technique to. And you can see that so this is the median value. On average, we can recover surface gravities of these stars to about 0.15%. We get radii to 1.5%, mean densities the same, masses to about 4%, and ages to about 10%. There's also a number of theoretical quantities on here that are perhaps of more interest to specialists, like how well we can constrain overshoot and undershoot. So in summary, we get extremely precise stellar parameters by doing asteroseismic modeling of stars. And so here's one example of what we can do with that information. We know that higher mass stars have convective cores and lower mass stars have radiative cores, but where is that boundary? Well, by characterizing these stars using asteroseismology, we can measure the size of the convective core, and we can smoothly determine the exact mass at which stars begin to develop a convective core. Of course, there's a metallicity dependence here, but I thought this was a quite neat result. What else can we do with asteroseismology? Well, we know that many stars evolve in binaries, especially as you go up in mass. Lower mass stars are also in binaries, but it's interesting to ask whether they form that way, which seems to be the most likely hypothesis. Well, by looking at 16 sig A and B, which don't interact, we can model them independently and get their ages. And in fact, their ages agree extremely well, which is just a neat application of asteroseismology. As I mentioned, 16 sig B hosts an exoplanet. Asteroseismology is phenomenal for exoplanets because asteroseismology gives us such precise stellar radii. In order to determine the radius of an exoplanet, you need to know the radius of its host star. And it turns out that, yeah, here's basically the best characterized exoplanets. There's a direct relation between the stellar radius uncertainty and the exoplanet radius uncertainty. And the best exoplanets basically have the range of radii that's given by, the range of host star radius uncertainties that's given by asteroseismology. So if you want to characterize an exoplanet, you might consider using asteroseismology. And this has led to some very interesting results. For example, this famous system Kepler 444, which is 11 billion years old, and that age is derived using using asteroseismology, and it's known to have 5 exoplanets, which has implications for perhaps life in the galaxy and other such things. Speaking of the galaxy, if we want to characterize the history and the development of the Milky Way, then we need to know the ages and the velocities of the stars moving through the Milky Way. Asteroseismology is also, of course, phenomenal for that. And so in this work, I looked at developing scaling relations for using even low-quality data with asteroseismology to determine things like their age and their radius. And so on the left, we can see that the age of a red giant star scales with Numax and the large frequency separation and the effective temperature. And another interesting result is that the radius scales inversely with Numax, which is the easiest quantity to measure. This is something we should be able to measure for stars throughout the galaxy and get pretty good radii of stars just from the detection of Numax. We can even get a little bit more exotic. So recently, last year, we published a paper where we looked at Cepheid variable stars. Now, these stars typically oscillate with just one mode. And with one mode, what can you do? Well, they're coherent oscillators that have a characteristic light curve shape. And using time-dependent pulsation models, we were able to determine that the shape of that light curve is fundamentally connected to the parameters of those stars. And so we used the neural network to connect light curve shape to properties like the mass and the radius of the Cepheid star. And because we can measure these light curves in other galaxies, for example, in the Large and Small Magellanic Cloud, we can then characterize these stars extragalactically. Now, so far, we don't have evolutionary models with light curves. But once we do, and that's a work in progress, we'll be able to attribute ages to those stars, which is one step towards trying to determine how other galaxies developed as well. We can take it even one step more exotic and test fundamental physics with asteroseismology. So Einstein's theory of general relativity says that the gravitational constant is, in fact, constant everywhere throughout space and time. But theories of modified gravity, like string theory, promote the gravitational constant to a dynamical quantity that can change throughout the evolution of the universe. Well, if the gravitational constant is evolving, that means that stars would have evolved in an environment that had a different strength of gravity. And so here, for example, I've plotted some evolutionary tracks of stars that are evolving with different gravitational strengths. And what we did was, so here on the left, you can see there's an HR diagram showing if gravity was, if the change to the gravitational constant is positive, or over here if it's negative. Now, in the HR diagram, you can't say much because these are relatively small changes in temperature, and we can't resolve that. But asteroseismically, if you remember, we can measure the large and small frequency separation to 1 microhertz accuracy or better. Precision, I should say. And so these same tracks that are over here get clearly separated in this asteroseismic diagram, which means that we can derive a constraint on the time evolution of the gravitational constant using asteroseismology. And in fact, that's what we did. We took an old low-mass star, approximately 10 billion years old, and we modeled this star, taking into account its mass, its initial chemical composition, and the convective parameters, nuclear reaction rates, in fact, because these can cause a degeneracy in the age, and the time variation of the gravitational constant. And from that information, we were able to put an upper bound on the change of the gravitational constant over time to be no more than 5 parts in a trillion per year. Now, this complements other experiments that have tried to measure the time variation of the gravitational constant. These are experiments like the lunar ranging experiment, which has measured over the past few decades the movement of the moon, but also measurements that probe cosmic time, like those from Big Bang nucleosynthesis and the cosmic microwave background, as well as constraints from helioseismology and white dwarf cooling. So from this, we can say that there's as yet no empirical evidence for string theory. Okay, now all of those interesting applications aside, what I'd really like to talk about now is how good are the best stellar models? Because all of the previous investigations that I've told you about, giving the ages to stars, estimating their radii, the applications to exoplanets, etc., these all hinge on our stellar models being correct. So in those investigations, we assume the truth of stellar evolution theory. Even more, we assume the truth of evolution theory as it is currently implemented in whatever stellar evolution code we're using for that purpose. But we'd like to test that hypothesis. And so here are my pet stars again, 16 Sig A and B, and their best evolutionary models. And on the right, you can look inside of the star, and I've shown the squared isothermal sound speed, which is simply the ratio of pressure to density inside of this star. And the question is this the right structure? Does stellar evolution theory predict the correct structure of these stars? So if we compare their asteroseismic frequencies, this is in a shell diagram. So on the y-axis, we see the frequency, and on the x-axis, we see the frequency modulo that large frequency separation. Now, as the large frequency separation is the spacing between modes of the same spherical degree, that causes these modes to line up vertically in this diagram. And you can see that qualitatively, the fit is extremely good. So you can say, I think we can confidently say we're not far off. But there are highly significant differences. Actually, if you actually subtract them off and divide by the uncertainty, you can see differences of up to 10 sigma, which again is a testament to the quality of the data. But also it tells us that the models are not exactly right because they cannot exactly reproduce the oscillation frequencies of these stars. And remember, these are basically solar twins. So we then have, what we want to do is we want to try to determine the internal structure of the star purely using the asteroseismic data without assuming the truth of stellar evolution theory. So the way we do this is that we take a reference model and we calculate the differences in the structure using the differences in the frequencies. So that's what this equation is saying. On the left-hand side here, we have the differences in frequency, and there's 55 modes for these stars. So there's 55 such equations. So you have one of the modes of oscillation, and you want to say the differences in these frequencies between the star and the model is equal to the differences in structure, so this is the difference in sound speed, times the sensitivity of that mode to those differences in structure. And here's an example of those sensitivity functions. We call them kernels for 3 different oscillation modes I've shown. And then plus, it turns out you need a second variable, so plus the differences in the helium abundance times the sensitivity to the changes in the helium abundance. Now, on this right side, I've shown the sensitivity kernel for the same 3 oscillation modes in the differences in the helium abundance. Now, fortunately, you can see that the sensitivity is only in the very outermost layers of the star. And so what we're going to do is try to make pinpointed measurements of the internal structure, for example, the density or the sound speed, in this case, the squared isothermal sound speed, at some locations in the stellar interior. And you basically know we can't do it here because, yeah, you have a conflict between the sound speed and the helium abundance, but in the deep interior of the star, we can isolate the effects of the differerences in the frequency to the differences in the sound speed. And in that way, we can measure the internal sound speed of that star, just like helioseismologists have done for the sun, and just like geologists have done for the Earth. Now, if these modes were a delta function, right, peaking only in one area, right, if the kernels for these modes were a delta function, then our job would be easy. If the mode frequency differed between the star and the model, we'd say, aha, the sound speed is different exactly in that location in the star. But our job's not quite so easy. And so instead, we need to do something to build up what we call an averaging kernel. So what we're going to do is we're going to add up the information from the different oscillation modes, add up their kernels in such a way that this linear combination of the kernels is sensitive only to one region in the star. And so I've drawn here what I call the target kernel, which is where we're trying to make this localized measurement. And again, I've shown the shell diagram, and I'm showing which modes I'm using to build up this averaging kernel. So far, I've added together the kernels of 4 modes, and you can see it's not localized at all. This won't tell us anything about the internal structure. Now I add 4 more modes. It gets a little bit better, but still, it doesn't help us to determine the internal structure. If we add some more modes, it seems to get worse, but eventually we get very kind of stabilized, and now you get something that appears to be able to you know, most of its sensitivity is to this region. And finally, when I add all the modes, you get what we call a well-localized averaging kernel. Now, this is basically an instrument that we can use. We can plug in the frequencies for this star, which, by the way, we have not so far used. We've only used the mode set and the observational uncertainties. So we've built up this instrument without even using the frequencies of the modes. Now we can plug in the observed frequencies of the modes and find out exactly how the speed of sound differs in this location in the star. So we've done this for 16 sig A and B. We looked at the differences in their frequencies and compared those to best fitting stellar evolution models. And actually what you see is pretty broad consistency. I mean, maybe there's a bit of a bias. The measurements are perhaps slightly indicating a slight difference, but from a statistical point of view, we can basically say that these stars, at least in their near core regions, don't really show a difference in internal structure with respect to best fitting stellar evolution models. So what we then did is we went to a slightly more massive star, one with a convective core. And right beyond the convective core boundary, we were able to make these measurements of internal stellar structure. And here we saw a somewhat different story. We saw that there was basically a gradient in the differences in the squared isothermal sound speed. And so up here in this diagram, you can see that the model sound speed is higher than the observed sound speed in that star. And down here, you can see that the model sound speed is smaller than the sound speed in that star, which might indicate that there's missing mixing processes from that star. So we tried to take it a step further and include some additional physics into our stellar evolution simulations to see whether these would remedy these differences that we've seen. So we tried looking at overshooting, so simply extending the convective core boundary in that star, but in fact this did not produce an effect that, resembles the shape that we're looking for. So that didn't help. And we also included diffusion. We also included both of them at the same time as well. But in fact, none of the things that we've tried so far has been able to explain the seismic structure of the star. So this is something of a puzzle. There appears to be somehow some missing physics in our stellar evolution simulations that's giving us the incorrect structure of this star harboring a small convective core. Okay, and then the last thing I'd like to tell you about is, which I guess I have a few minutes, right? The last thing I'd like to tell you about is our attempts to go a little bit further in evolution. So far these have been main sequence stars. And so what we tried to do next, here's a simple evolutionary diagram of the sun. We've been doing stars that are here. What we tried to do next is look at subgiant stars. Now, as I've been telling you, the stars that we look at oscillate with P modes. In particular, you know, they oscillate around this quantity that I called numax, and so these are all acoustic waves. Now, Connie and her group are mostly looking at stars that oscillate with G modes. G modes have not been observed in the sun, despite claims almost every year that they have. But what's interesting about subgiants is that eventually the frequencies of the P modes become of order the frequencies of the G modes, and this presents the opportunities for these different types of oscillations, these different types of oscillators to couple and produce mixed oscillation modes. So here's an animation I've prepared for you that shows you exactly what happens. So in this top left panel is an HR diagram, and you'll see the evolutionary track of a star as it becomes a subgiant, one that's slightly more massive than the sun. You can also see this is the solar position. Down here, I'm showing the frequencies of oscillation as it evolves over time. You can see this extremely regular pattern, and yeah, I'm only showing the radial modes and the dipole modes. Up here, you can see the sound speed kernel for one oscillation mode, and it's shown in log space looking into the star. And so you can see the oscillations, the kernel of this star is mostly sensitive to the sound speed in the outer layers of the star. That's why we could resolve, for example, the sound speed at 20% away from the stellar center, but not closer in, and that's because the data only allows us to peer that far in. By the way, that's also the situation with the sun. We can't look into, let's say, the innermost 1% of the sun, just because the modes don't have great sensitivity there. And here's another propagation diagram like the one I just showed. You can see the observable region. You can see the Lamb frequency, which tells us where the P modes oscillate, and you can see the buoyancy frequency, which tells us where the G modes oscillate. Now we can watch this evolve. So we're firmly on the main sequence. Oh, I'd like to pause if I can, actually. Okay, so far we've already seen some evolution. Now that we've become a bit of a subgiant, you can kind of see it here, but not really very strongly. I've colored the regions of nuclear generation. So as you know, as a star evolves off the main sequence, it goes through its supply of core hydrogen and continues fusing hydrogen in a shell. And that's what you can see here, this shell hydrogen fusion. And the buoyancy frequency is peaking in this hydrogen burning shell. And so what's going to happen now is, I'm going to continue the evolution. What's going to happen now is, as this bumps into the observable region, you're going to start seeing avoided crossings of mixed modes over here. Here's an avoided crossing, here's an avoided crossing, and look at our sound speed kernels. They're developing extreme sensitivity to the inside of the star, inside of this inert helium core. And so now in this, highly, in this, oh boy. In this, this burning hydrogen shell, you have this peaked buoyancy frequency, and so you get this mixed oscillation mode pattern in the frequencies, and the dipole modes then have a G-like character in the interior and a P-like character in the exterior, which means we can use these modes to measure deep into the star. And so that's what we've done in a paper we published this year. We were able to form these averaging kernels by adding up the oscillation modes, not only from the radial modes, but also from these mixed dipole oscillation modes that allowed us to form averaging kernels that are peaked in this inert helium core, in the hydrogen burning shell, and we can get some broader ones in the radiative zone, which is allowing us to make measurements deeper in another star than we're able to do in our own sun. And so finally, I'd like to share with you some new results, never before seen, of a star that we've been looking at. This is not from the Kepler mission, it's not from TESS, it's actually from the SONG satellite. SONG is a network, sorry, I said satellite. SONG is a network of ground-based telescopes that observe one star at a time. And I think so far there are 3 SONG nodes. And they've mostly been they've observed a lot of different stars, but the very best star is the star Mu Herculis, which has 6 years of observation, so 50% longer than Kepler. And this is allowing us to make the best observations of a subgiant that's ever been made. And from that, we've been able to deduce the structure of its helium core. And what you can see here, these are the smallest error bars I've been able to see in asteroseismology so far in measuring internal stellar structure. You can see that the inert helium core, the sound speed in this star is much lower than is predicted by stellar evolution theory. Now the sound speed is, here it's the ratio of pressure to density. Now in a subgiant, you don't have an ideal gas because you have some partial degeneracy, but if it were ideal, you could then say, okay, pressure over density, that's then the temperature over the mean molecular weight. The mean molecular weight is fixed because the core is pure helium, and therefore this is a temperature difference. Now, it could be a temperature difference, or it could be an equation of state difference. Either way, we are seeing now some fairly compelling evidence that the models of these stars are producing the incorrect core structure of subgiants. And this is, of course, of importance because that's the phase of evolution that our sun will progress into next. Before I finish, I'd just like to highlight some junior scientists that I've had the pleasure of collaborating with. Now, the slide says students, but of course, Mark has graduated now and gotten a Hubble Fellowship, and Sushmita has also graduated now. But yeah, so I've been working with a lot of these wonderful students, and we're doing things like trying to do these inversions on even more evolved stars, on red giants. We're doing 3D models of stars. We're doing lots of machine learning. Yeah, I've also just started working with Vincent in the audience doing inversions for more massive stars, which is extremely exciting and promising. So in summary, asteroseismology allows us to measure the internal stellar structure. It gives us ages, masses, and radii, which are broadly useful throughout stellar astrophysics, and it actually allows us the opportunity to test the physics of stellar evolution, which is a very exciting prospect. Thank you for your time. Sorry, can you say again?
The kernels?
Yeah.
How do you, can you calculate them analytically, or do you need hydrodynamic simulations for those?
Yeah, very good question. Yeah, right. 1 second. So the question is about the structure kernels. So the kernels actually come from the reference model. So in order to do this calculation, we basically want to assume the equations of stellar structure and the equations of stellar oscillation, but not necessarily the equations of stellar evolution. So we take a reference model, which happens to be an evolutionary model, but it could be any model. And there have been studies to saying, you know, how sensitive are the results to the chosen reference model. At least in the case of the sun, it's very insensitive. You need something reasonable, something that oscillates at least roughly in the way that this star oscillates. In fact, these are linear kernels, so they should be in the linear regime, meaning that a linear change to the structure should result in a linear change to the mode frequencies. So what you do to get these kernels is you take a reference model, you take a model with a given structure, and you basically calculate. You can derive the equations analytically, but we do it numerically with a numerical stellar structure. You perturb the equations of stellar oscillation, and from that you can work out what these kernels are, what a perturbation to any quantity does to the frequency of that mode. And so that's how we get the kernels.
So to finite difference then. So it is a numerical derivative.
Yeah, so for these particular kernels, actually, we do numerical derivatives, yeah. I can also encourage you to read Vincent's master's thesis, because he has actually just re-derived the kernels and derived new kernel pairs, which is very nicely done.
I have a question on your lack of mixing.
Yeah, so on...
That sounds familiar.
Yes.
And so...
On this, or...
Yes, I wonder if it would be a lot of work for you if you look at Mied Peterson's Nature Astronomy paper. There we really need, different ways of mixing than what you have used standardly here from ESA. So penetrative convection and also different envelope mixing.
Yeah.
It would be really interesting if you use that instead of the classical overshoot that you have used.
Absolutely.
Yeah.
Yeah.
It'd be too hard for you, right?
We should do this. Absolutely. Should I repeat for the audience? Yeah.
That couples back to the question, how sensitive are you to where you are in the evolution?
Yeah.
Because it doesn't matter for solar type stars, but it does matter for Leuven stars.
Yeah. So for those following at home, Connie's suggestion is to do as Mied Peterson has recently done in her nature astronomy work, which is to consider different types of mixing that can go on in the stellar interior. And what Mied was able to show is that for these massive stars that they've modeled, if you include these different types of mixing, you can get much better fit to the observed frequencies. And so the suggestion is to repeat that for this kind of star, which I agree, that's an excellent suggestion. I think we should definitely do that. Yes, that's an excellent question. So the question was that so far I've shown that there's some discrepancy between these one-dimensional stellar evolution models and the observed structures of these stars. and what is the path forward, essentially. Is it the fact that we're using 1D models? Is it microphysics? Or what else? So there's a few different avenues that we're taking to try to remedy this. So first of all, the sun is an excellent constraint. And in the sun, as I mentioned, we have some 60 sigma disagreement at the base of the convection zone. Now, there's probably two main factors contributing to the discrepancy in the solar structure. The one is that we're using this simplistic treatment of convection in 1D models. So we use the mixing length theory, which, you know, we just have the classical Schwarzschild boundary and no convection proceeds past that point. But probably it does, and so one of the students that I'm working with, Mark Winther, is doing his PhD. He's making a full 3D model of the sun, not just some small part of the sun, but the entire sun, with the hope that perhaps, you know, this is an MHD model using the moving mesh code or repo. The hope is that with that, we'll be able to resolve the convective boundary a lot better and hopefully recover a better sound speed profile. Now, also in the sun, the great feeling among helioseismologists is that we have the microphysics wrong, that particularly the opacities at the base of the convection zone are inappropriate. I think it's the opacity of iron at 2,000 Kelvin or so could be improved. And so we're also working on, we're working with some people who are doing the opacity calculations in hopes that they'll give us updated opacities and we'll produce a better solar model. Now, in the case of these stars, the differences run deeper, mainly because we can only resolve the near core region. In this star, I think that there's probably missing mixing, and I think Connie's suggestion is an excellent path forward to incorporate these other types of mixing that we know should exist in the stars but are not incorporated into 1D stellar evolution models. In the case of the subgiant, it's a little bit more tricky. I mean, you have a pure isothermal helium core. And so what can you do with that? Well, one thing is that the opal equation of state might not be correct. It might not be incorporating properly the degeneracy pressure. And so I've now started talking with Achim Weiss at MPA, who has a more sophisticated implementation of an equation of state, and we're going to try to see if we can improve our models through that. So this might be indicating an equation of state problem. Other than that, it's a little bit difficult to see what could go wrong in the core of a subgiant. You don't have too many degrees of freedom. I mean, there could be a small metallicity effect. The mean molecular weight will change, and that'll change the structure. But other than that, it's not like you have some kind of valve that adjusts the temperature. Now, of course, the temperature earlier on the subgiant branch, the core temperature is lower. So it could be that somehow the core is young, but the envelope is old. How you get that's also somewhat of a mystery. So this is quite a new result, so we haven't had the chance to do all the fun experiments yet, but I am looking forward to trying to figure out exactly what's going wrong in our models for this star. Yeah, so the question is if, for example, the main sequence evolution is going wrong, and that's leading up to the incorrect structure of the subgiant. That's, of course, possible, but the question is what is going wrong? And it could be, in fact, that it's exactly this kind of thing that's going wrong, you know? Maybe this is the silver bullet. If we incorporate these additional types of mixing on the main sequence, we not only get improved main sequence models, but that carries through towards later stages of evolution. How nice that would be if that turns out to be that way. I'm looking forward to testing it out. So far, I'm not that lucky, but that would be great.
Can you publish that?
Yeah, this new one? Yep. Oh, yeah, exactly. Yeah, I'm working on getting it out. Yeah, this is an exciting result. Okay, increase the convective core mass.
Go back in time, increase the convective core, because that's what your mixing is doing, and then you can tell us how much mass you miss in the convective core. I predict you, and I bet you it's not too different from these things.
I see, I see. So in the main sequence of this evolution, increase the core size and see if it fixes it.
The mass,
Increase the convective core mass.
yes.
I see. Okay. Interesting.
Keep adding mixing it to increase the core mass, and then tell us how much mass the core should have by the end of the main sequence to reproduce the observable.
Okay, interesting. Sounds good.
I'm almost sure you will solve it.
Okay, fantastic.